All right, our next lesson is called Form and Function. And the main purpose of this, or the main idea here, is that functions show their faces in many ways. And this is very related to the problem we did earlier with the banquet tables, because we noticed that various people could have seen a pattern or seen it building in a different way, and therefore it leads you to possibly coming up with a different formula. But we showed how different formulas, so the order is different technically, right? And they're written differently. If you simplify them, actually turn out to be exactly identical. So we're going to focus on that in this lesson. Prior knowledge for this particular lesson would be remembering what input-outputs are, function notation, which that's this f of x notation, and how it relates to inputs and outputs, and then again what an identity equation is, okay? And we'll be talking about that more and more. We'll be using identity equations in that idea. So for now, let's go ahead and start with a warm-up. Okay, so I'm going to give you a function rule right here. And f of x equals x times 2x plus 6. And don't forget what this is really saying. It's saying, okay, in order to get an output for this rule, I need to take the input, and it looks like it says to take the input and take itself, and multiply it by 2 times the input plus 6. So this one's built on the product of two separate pieces that they do their own calculations for. So go ahead and pause the video now. I want you to work on finding A, B, and C here. Then we'll come back together and do them and then move into the next part of it. Let's look at the solutions here. So f of 0 means our input is 0. And since the rule says take your input and multiply by twice the input plus 6, we can just literally write it down what that says. And if we think about this, this is 2 times 0 plus 6 is 0 plus 6. So this ends up being 0 times 6. Although, honestly, we could just look here. It says 0 times whatever, and I think we all are okay with 0 times anything is still 0. So in the end, you should have gotten 0 there. B is an interesting one. It says another input that makes f of x 0. So actually, remember how 0 gave me an output of 0 for this function, and it's actually asking me the reverse. If I want an output of 0, what's another input? Which means, well, we have one input that makes an output of 0. But what's another input? This one's going to take a little bit of searching, I think. But if you look at the fundamental structure here, this function is built on, like I said earlier, a product. In this case, the input times twice the input plus 6. Well, we already found out that putting 0 right here makes all of it be 0. And maybe you thought, hopefully you've come up with, well, there's a number that should make this piece 0, hopefully, because then times anything is still 0. So if that's something you didn't understand, maybe you want to pause again and try that one now that we've talked about it a little bit. But anyway, I think it's going to be, let's see, if we play around with some numbers here, well, if you think about it, this whole thing itself should be 0, shouldn't it, guys? Right? Because we found out if this is 0, the whole thing's 0. But also if that piece is 0, the whole thing's 0. So actually there's like a kind of a more like an equation way to solve it. I can make a separate equation. We know that this other piece being 0, the whole thing being 0, will make that work. And maybe you can do this in your head. I'll tell you, the answer is -3. You might have just kind of figured that out. But this helps me find exactly. And then if I solve this, 2x equals -6, then divide by 2, x equals -3. And we can always go back and check that. Because if I put -3 for x here, I get -6 plus 6, which is 0, and -3 times 0 ends up being 0 again. So we answered the question. And then C is pretty straightforward again, kind of like part A, f of -5. So -5 times 2 times -5 plus 6 is -5 times -10 plus 6, which is -5 times -4. And that's going to give us positive 20. Okay, so go ahead and just double check your work. Let's get into the main part of the lesson, and we're going to start out by looking at one example, and again, it's a many ways example. So I'm gonna write that on the board, and we're gonna go ahead and start thinking about that together. Example, here's a table of inputs and outputs. And we've got the inputs from 1 through 5, we've given you the outputs. Can you find the next output? So right here, when the input is 6, what's the next output? Right now what I want to encourage you to do is, first of all, just try to find that output in any way possible. Look for any patterns you can. And after that, I really want you to spend some time brainstorming. So I would want you to spend maybe 5 to 10 minutes actually, even if you already find that output pretty quickly, to try to brainstorm as many ways as you can think of to figure that out. There might be one way you come up with that sticks out to you, but then I want you to think about, okay, well, is there any other relationship I can figure out between maybe the inputs and outputs, or going from one output to the next, or anything like that, and try to come up with maybe at least 2 ways if possible, and we're going to look at a bunch of the different ways together. But for now, I want you to go ahead and pause your video, and I want you to take some notes on trying to figure this out for yourself right now. And I encourage you to work with a friend. That'd be totally okay. In fact, that's even better probably than thinking about it yourself. And then we'll come together and look at this. So go ahead and pause right now. Okay, so I guess what I'm going to do here, guys, is I'm going to extend this table a little bit. And I'm just going to make kind of a new column to talk about the different ways, I guess. Now, just to be clear, I'm going to talk about one way, and I'll probably put how the numbers work here, but to avoid clutter on the board, I might not put all the different ways here. So you can, in your notes, kind of organize this yourself and put the different ways separately, okay? So let's first of all talk about one thing I see students often do is kind of realize if we move up, or check if we move up from one output to the next, to the next, to the next, to the next, what's happening. And in fact, I'll just tell you the answer right now, just to see if you got it right. The answer is 48 for the next one. And so the first different way, a first way we could look at this to figure this out is just to simply see, oh, I've added 3 here, and from 3 to 8 I've added 5, and from 8 to 15 I've added 7. Maybe you see where this is going. And here I've added 9 to get there, and then 24 plus, in this case, 11, and then, again, if we believe that pattern keeps going, I guess, then 35 plus 48, 35 plus what should give me there? 35 plus 13 gives me 48. So to continue this pattern of going up by the next odd number, it seems like, that's one way to view this. And that is a very natural way a lot of us see things like this. So we look for patterns and how do I make it from one step to the next, to the next, to the next. And that is totally great if you saw that. Now what gets a little bit tricky here is another way, I guess, right? That's always difficult. This isn't really an easy problem, but I just want you to really think about it. Okay, so make sure you have that way written down, and I'm going to go ahead and record another way that you could look at this. Well, I almost see this, and I've seen students pull this out before, as like breaking down. I'm actually going to leave the 0, but breaking down, we're going to kind of see every output as, and I'm probably going to leave these arrows here just to indicate we're talking about how they break down. The rest of the ways are going to look at the input-output relationship. Notice the last one, we didn't really specifically talk about the inputs and how they relate to the outputs. But this is more like if you're trying to build a formula, all the rest of these ways. And again, if I get to this, one of these ways, and a light bulb goes on, oh, and you want to try looking for more, then go ahead and pause and look for more. So I see 3 as 1 times 3, and 8 as 2 times 4, and 15 as 3 times 5. Maybe you see where we're going with this. And 24 as 4 times 6, and 35 as 5 times 7, and 48, let's see if this pattern actually keeps working. What will come next? 6 times 8. Doesn't that seem like that's true? Is that right? So that's a really crazy way. Another way, it's all about being flexible with breaking down numbers. Remember we talked about what algebraic thinking is? This is totally algebraic thinking, even though I haven't used a variable yet, right? So doing algebra is more like the way you think about numbers, not just using variables. So that's one way to think of it. And so what I actually am kind of curious about now is if we kind of let this go down and become n, what would be the formula for our f of n? If you get what I mean. Okay, so if I kind of made this look like that. So let's take a quick look here. Let's go back and look at how do we think the n that I'm on relates. Look, when n is 6, it's 6 times 8. When n is 5, it's 5 times 7. When n is 4, it's 4 times 6. When n is 3, it's 3 times 5, etc. And in fact, actually, maybe we should go back here with the 0 now and put in, if we fill in the rest, it seems like this, according to the pattern, would be 0 times 2, technically. Do you agree? 0 times 2 still gives me an output of 0? Yeah. So it seems like this left number is exactly the same as the input. So if my input's n, it seems like I should have n times something, right? Well, how does this second number relate to the first number in every single case? If you look really carefully, the second number is always 2 more than the first one. So it seems like we're building a formula for this function. F of n is n times n plus 2. That's really cool, huh? So there's another way to look at this. I'm going to go ahead and erase this, and let's look at 2 more ways of looking at this. So make sure you have all these ways written down. And again, if anytime you want to pause and look for more now that you get maybe a better idea of what we're looking for, then go ahead and do that. So another way that I've seen students come up with is actually realizing, if you look really carefully at all of these numbers, they're actually one less. Each one of these is one less than a very special kind of number. What I mean is, if you add 1 to all these numbers, why don't you go ahead and think for yourself in your head what's going on if we add 1 to all these? We get a new sequence of numbers that's very familiar. So, if we add 1, this is 1, and that becomes 4, 9, 16, 25, 36, and 49. Do you recognize those are the perfect squares? So watch. It seems like this is 1 squared minus 1. Remember how we said it's 1 less than that perfect square? And 3, it seems to be 4 squared minus 1, and then 4 squared, whoops, 3 squared, no, 2 squared minus 1. It's 4 minus 1, whoops. And then 8 is 9 minus 1, so that's 3 squared minus 1. And then this is where we get the 4 squared minus 1, 16 minus 1. And then 25 minus 1, so 5 squared minus 1, 6 squared minus 1, and 7 squared minus 1. And again, a challenge right here is, okay, now that we recognize that pattern, which is also really interesting, again, is there a formula? If my input is n, let's look real quick. If right here I'm at n equals 6, but that was 7 squared minus 1. When n is 5, it's 6 squared minus 1. Notice that whatever the n is, this number here is 1 more. That squared number is always 1 higher than the n I'm on. So it seems like I'm squaring 1 more than the input. Okay, that's saying a lot, but 1 more than the input, if I'm squaring it, and then all these are just subtracting 1 off the end. So there's another way to see that function, actually. Okay? Keep track of these because we're going to actually come back to them afterwards. Let's look at one last one. There's many more, although as far as ones that have a really cool, way of seeing them, I guess, or simple, I would say, because you could make this really complicated if you wanted, but simpler ways, we're going to have one more simpler way. Let me double check real quick to remind myself. Okay, this one maybe won't be as obvious, I would say, but this next one still fits. And I've actually had, believe it or not, I've had students come up with this. This isn't one I would necessarily say you would notice yourself, but so notice here my n is 1. I've had students actually see this. They've seen this as 1 squared plus 2 times 1, and 8 is 2 squared plus 2 times 2, and 15 is 3 squared plus 2 times 3, 24 is 4 squared plus 2 times 4, and then 5 squared plus 2 times 5 to get 35. Oh, and I guess we have one more. 6 squared plus 2 times 6. Look carefully yourself. And again, I wouldn't expect necessarily you to come up with this one. And I suppose if I keep this pattern going, 0 squared plus 2 times 0 for that one. But at least confirm in your head that this calculation really is equal to those outputs. Okay? And once you've done that, so again, 6 squared is 36 plus 12 is 48, etc. Well, let's go ahead and go back. Again, we're always going to ask ourselves, if this is my input, how did this number pattern that I noticed relate to that input? And actually this one, as far as this pattern goes, you can literally see whatever the input is, whatever n is, you can actually see it show up in the calculation. So a couple of these numbers are varying, they're variable here, and one number is staying constant the whole time. What number is staying constant the whole time? This 2 right here, all the way down, is staying as 2, right? So it seems like I have something squared plus 2 times something. But the good thing is, it looks like it's directly, literally just n. So n squared plus 2 times n is another one that you could see from these numbers. So let's go ahead and draw these out on the board, each of the ones I came up with, and we're going to talk about this property here, or this idea, is that functions show their faces in many ways, even if one function is still always going to take the same inputs and make the same output, even if the rule looks the same. We're going to talk about showing how the rule really is the same. Three formulas we came up with. Now, I know the very first way that we thought about to find the next output, that wasn't necessarily based on using the input itself, like in a way we could make a formula right now. And it's a great way to notice patterns, but that one itself, and you could even think about the banquet table problem, that way, what if I asked you to find f of, 100? What if I asked you to extend the table all the way down here to when n is 100? It'd be a real annoying pain in the butt to keep that adding pattern going and add all the way until I get to 100, right? So having a formula is great because then you can plug 100 in for n and do the calculation like that without having to do like all that adding repeatedly over and over or whatever the pattern is, right? So we're going to look at all these three, each of these three different rules that we came up with, and we're going to see something interesting. Now, something you're used to doing is writing at this point is, well, we learned multiplying algebraic expressions. So this one involves a perfect square we're going to have to multiply out. This one is fairly easy to do the distribution. And then this one, actually, you might recognize it's kind of already in the fully multiplied form, I guess. You might think of it as simplified, although neither one of these is necessarily more simplified than the other one. But this one is the fully multiplied and out one and all the, combined like terms and everything. So this one's pretty easy to start with. If I actually distribute, n times n is n squared, right? And so this becomes n squared plus 2n. And guess what? Wait a minute. That ends up being the same as the third way we looked at. And let's take a look at this one. If I actually do n plus 1 squared, hopefully you remember our pattern is a squared plus 2ab plus b squared. So if you remember the pattern, this is going to be n squared plus 2 times n times 1, right? 2ab plus b squared plus 1 squared, which is n squared plus 2n plus 1. Now, don't forget though, there's this minus 1. So in the end, I'm going to put a minus 1 and a minus 1. And I get n squared plus 2n, because that plus 1 and minus 1 cancel out. And again, this is still the same as that. So that's really crazy. And that's what the whole point here we talked about of our lesson today is realizing that functions and number patterns can be viewed in many ways, but if it's the same number pattern, if you find a rule or a formula for the function, they all must actually agree and somehow be able to be simplified or rewritten in the form of the other one, okay? So, this is the same and this is the same. So what it means is, no matter which of these rules I actually started with using, if I plug an input in, let's say 3, every one of those formulas will spit out 15, even though they're actually technically a different order with different calculations. And that's really mind-blowing, to be honest. One thing you could have done here, though, just to mention, I didn't write it out, is you could still use your expansion boxes to get to expand this n plus 1 squared, and you get n squared and 2 n's and 1. So n squared plus n makes 2n plus 1, and I would get that. Okay, so let's pull together and do a few more examples before this. We get to officially put in words our rule here that goes with our lesson, our main thing. It's called form implies function, okay? And form means what form an expression is in. And if that form can be shown to be equivalent for two expressions, then they must be the same function. That's why we call that rule form implies function. And this is the official way of stating it. If two expressions are equivalent under the basic rules of algebra, then they define functions that produce the same output for any given input. So even if the rules themselves are technically different, it means they technically make the same function as each other that gives the same inputs for the same output. So right, if I were to technically call this f of n, it's the same function from my last example. And if I wanted to call this different function a different name, like g of n, well, it's just like we said before. If I wanted to calculate f of 3, watch what happens. It's 3 times 3 plus 2, which is 3 times 5, which is 15. This one is a different function technically, right? And if I want to do g of 3, it becomes 3 squared plus 2 times 3, which is 9 plus 6, which is also 15. So even though the order of the calculations is different, and honestly, it's not, like I said, it's not even really the same exact thing, directly, it turns out since one of these can algebraically be manipulated or shown to be the same as the other one, in fact, we could go either direction, then it must always be true that if you put an input into one, you're going to get the same output as if you put that same input into the other. That's a really, really important thing. There's another example we could look at, I guess, just because this is good review from what we have done recently. What if I had a different function, or whatever, expression? Let's say we have x plus 3 times x minus 8. We've learned about multiplying these together. This would be a good opportunity for you to pause and check for yourself that you know how to multiply this out. But if you multiply this out, you're going to get x plus 3, x minus 8, x squared, and then 3x goes here, and minus 8x goes here, and then negative 24 when I multiply those. So remember, I'm matching each with each, right? So in the end, don't forget, these two diagonal ones are always going to be like terms of x as long as it's set up in this way, right? With just x and a number and x and a number. So 3x plus negative 8x is minus 5x. So I should get x squared minus 5x minus 24. And we can check the same thing. If I were to think of this like f of x, let's say, but the right side like g of x, you and I both know that they're equivalent, but we can just make sure we're good with plugging in some number and seeing that you get the same output. Let's try f of 2 or something like that. Well, here f of 2 is going to be equal to 2 plus 3 times 2 minus 8. And that's going to be 5 times negative 6, which is going to be negative 30. Whereas this one, if I do the same input, g of 2, I should get the same output, right, as I got here. So that's going to be 2 squared minus 5 times 2 minus 24, which is 4 minus 10 minus 24. 4 minus 10 is negative 6, minus 24 is negative 30. It's the exact same thing. And it doesn't matter what input you tried, as long as you have an input that works in each function, right, and you plug it in, you're going to have to get the same output, because we showed that the algebra works out to show that the two expressions are equivalent. So they are actually identical.